We've been working the last couple of units on graphing linear equations and talking about linear functions, rates of change, starting points, slope, all of that sort of stuff. So we've learned how to graph lines really well. We're now going to look at a really cool use of graphing lines to solve a completely new type of problem that you probably have not seen before. So the I can statement for 6.1 is I can solve systems, so go ahead and write the word systems of equations by graphing. Solving systems of equations by graphing. That's what we're going to focus on for this unit. We're going to learn all about this topic, and there's a warm-up here. We've talked about these ideas before. I hope these ring a bell. These are things that if you remember these, they will come in very handy in some of the strangest places you might see. You'll go, oh gosh, I remember that from 8th grade, and it'll really serve you well. So the first two kind of go together. The first one says on A, if a point works in the blank, then it's on the blank. So if a point works in the equation, then it's on the graph. So if a point works in the equation, then it's on the graph. Meaning if we plug it into the equation and it makes the equation true, then it would be on the graph. And if a point is on the graph, then it works in the equation. So these go forward and backwards. Sometimes we say this is the converse of each other. So if a point works in the equation, in other words, if it makes the equation true, then it's on the graph. And if a point is on the graph, then it's got to work in the equation. It's got to make the equation true. And then the other thing to keep in mind that's going to be really useful as we talk about solving systems of equations by graphing is this. A graph is a picture. A graph is a picture of all the points that work in the equation. Again, when we say work in the equation, what we're talking about is it's a picture of all the points that make the equation true. Okay, so if we keep those couple of ideas in mind, it's going to make this particular topic a lot easier. So let's talk about what a system of equations is. So if somebody talks about a system of equations, it's a set of two or more equations. Normally we only solve one equation at a time, but in this particular unit we're going to be solving two equations, and the name we give that is a system of equations. So when we solve a system of equations, here's what we do. We find a solution that would work in all of the equations at the same time, and the most basic way to do this is we solve these by graphing. Okay, so we've got to make sure that whatever answer we get works in all of the equations, so it's got to work in them at the same time. Sometimes you might even hear this referred to as solving a system simultaneously. So it's got to work in all of the equations at the same time. So I've got this color coded a little bit, and you'll notice that I've got a graph right here. It's got dots on it, so we've got a nice grid pattern that we can work with. We can be really accurate with this. It says solve the system by graphing, and each one of these is already written in slope-intercept form. We know how to graph things really well in slope-intercept form, so I'm going to make sure I do this first one in red. This one crosses the y-axis at 4, and the slope is -1, so that would be down 1 and over 1. We've got this perfect 45 going down in this direction. Okay, I'm going to skip a couple. Goes like this, and we're just going to draw that line right there. We're going to connect those, and even if it's not perfect, we're in pretty good shape here. I could always take this and use my line tool. I probably will do that at some point, but this should be okay for right now. I'm now going to switch colors, and we're going to do this one right here. So I'm going to do in blue, the y-intercept is -2, so here's our starting point. This is what anchors us. And then the slope on this one is +1, so we're going to rise 1 and run 1, rise 1, run 1, rise 1, run 1. We're going to go like this. It's going to look something like that. Again, perfect 45 going in the upward direction, anchored at that -2. So we draw a line that goes like this, put an arrow on it. Okay, now let me make this clear. This is where this whole idea of keeping in mind that each one of these graphs is a picture of all the points that works in that particular equation. So this red graph here, this red line, is a picture of every single point that works in the red equation. And this blue line here is a picture of all the points that work in the blue equation. So if all of the red points work in the red equation and all of the blue points work in the blue equation, we want a point that happens to work in both of them. So if you take a look at this, there is one on here that would work in both of them. In fact, we actually graphed this when we were doing both of them right here, right where they intersect. So that point happens to be, let's write it down, over 3 and up 1, so that would be 3, 1. So this right here is the solution. That's it. So I do want to point out that there is a specific way that we want to write these. So once we know what the solution is, how should we write it? Well, we could just write x equals 3 and y equals 1. I mean, we could write that, but we normally write them as ordered pairs, because what we're doing is we're finding the point where the lines cross, and points are xy pairs. So although we could write this as x equals 3 and y equals 1, it's probably best to write this as an ordered pair, and then everybody knows the first one is x and the second one is y. And the second thing is, what can we do to check our answers? Well, to check our answers, let's do this. Like we learned before, plug it in to both equations. So we want to check and make sure that it actually works in both equations. So I'm going to change to red, and we're going to plug in, remember this is going to be x and this is going to be y. So I'm going to put a 1 in for y and a 3 in for x, and I'm going to do that right here. So in red, this is 1 equals negative, we're plugging in a 3 for x, plus 4. So this is 1 equals, this would be negative 3 plus 4. We get 1 equals 1. So that works there. It checks out in the blue one, or sorry, the red one. Let's check the blue one now. So we're going to put in a 1 right here. We're going to put in a 3 right here, and then we'll subtract 2. So we get 1 equals 1. So that one checks out. So it does work in both. Now, if we graph these accurately, we don't always have to check that, but it would be a really good idea to do that, especially if we were taking a test or something like that and we kind of wanted to guarantee that we were going to get it right. So let's take a look at the next one. Again, I'm going to do this in 2 different colors. This one crosses at 2 on the y-axis. There's our starting point. We're going to rise 3 and run 2. So rise 3, run 2, rise 3, run 2. We're going to go down 3 and back 2, down 3 and back 2. So it's going to look like this. We'll draw as straight a line as we possibly can. Switch colors, and we're going to take a look at this other one. It crosses at negative 4. So it crosses right here. And the slope is negative 3/2. So that means we're going to go down 3 and over 2. We've now got to go the other direction. Up 3 and back 2. And notice what we've got right there. Up 3 and back 2. That is enough that I can draw the line. I really don't need to do much more than that, because I know if I draw a straight line, because this point right here was a point that I graphed on both of them. Okay, so it was used in that stair-step pattern when we were going down 3 and back 2, and when we were going up 3 and back 2. So those line up perfectly. So this point right here would be back 2 and down 1. So there's our ordered pair. If we wanted to write it as x equals negative 2 and y equals negative 1, again, that would be okay, but the ordered pair is much better. So I'm going to write negative 2 comma negative 1. And again, this is a much quicker way to write this, because if we've written it as an ordered pair, we're kind of telling people, look, we understand that we're solving a system. These are 2 lines, and we're trying to find the point where they cross. And it's much quicker for people just to assume that this one's the x and this one's the y. So we've got our answer right there. Okay, let's take a look at the next one down here. So I've got example 3. And we've got this one crossing at negative 1. So we're going to make this one cross at negative 1, and the slope is 3/4. So we're going to rise 3 and we're going to run 4. So be careful as you're graphing these. You want to do these as accurately as you can. We've got that little stair-step pattern for the rise and the run. So now instead of going up 3, we're going to go down 3 and left 4, down 3 and left 4. So there is the red equation. There's a picture of all the points that work in the red equation. And let's see what we've got on this other one. On the blue one, this one crosses at positive 1, and the slope is also 3/4. So we're going to rise 3 and run 4. We're going to rise 3 and run 4. We're going to go down 3 and back 4, down 3 and back 4, and we're going to get this right here. Now, if the point of solving a system of equations is to find the point where the lines cross, or the point that would make both of the equations true, if the red line is a picture of all the points that work in the red equation, and the blue line is a picture of all the points that work in the blue equation, stop and think about this. These both had exactly the same slope, so we're going to continue this stair-step pattern. Are these ever going to cross? And if they're never going to cross, what should we write? So think about that for just a second. I'll give you an option. It's one of those weird answers. It's either infinitely many solutions, which means any point that works in one would work in the other, or it's no solution. So stop and think about what it might be. Well, if these are never going to cross, they're never going to have a point in common. So on this one, it's no solution. Okay. You might spend a little bit of time thinking about what infinitely many solutions would look like. We probably will talk about that at some point, but we don't need to do that today. Let's take a look at the next one. We're going to graph this one here. So this is 3x plus 5. So it crosses at 5. Slope is 3, so rise of 3, run of 1. Okay. Down 3, back 1, down 3, back 1, down 3, back 1. So it looks something like this. Okay. And then we've got the other one is the line y equals -4. Now remember, if you've got y equals a number, that tells you where it crosses the y-axis, and x can be anything you want. So this is going to be a horizontal line. The slope on that would be 0. So I'm going to go forever in that direction and forever in this direction. And then we want to say what the point is where they cross, if they do. So on this particular one, they cross right here. Now, it's important to be as accurate as possible. I got a little bit sloppy with this. So let's figure out where this is. We would go back 3 and down 4. So the answer on this one, and again, we're going to write this as an ordered pair, would be -3, -4. Now, there shouldn't be any surprise about this right here, that the y coordinate is -4, because the only y value that will make this one true is -4. Okay, so keep that in mind. Now, let's take a look at the bottom of the page here, and it says, solving a system of equations by graphing, it can be a bit of a pain. We have to graph each one of them. You'll notice that each one of the lines that we graphed, they were already in slope-intercept form. They were pretty quick to graph. But you do have to graph both lines perfectly. Got to do them both perfectly. And if the lines don't intersect at a nice point, you can't get the exact answer. Now, on every single one that we did here today, every one of them lined up. So this lined up at -3, -4. These two lined up. This one was at 3, 1, and this one was at -2, -1. So they lined up at some nice points. But what would happen if they crossed at a point like this right here? We'd kind of have to take a guess or estimate, and we'll talk about what we do with those. Now, if something like that were to happen and we wanted to solve exactly what the answer was, there are some algebraic techniques that you'll learn in 9th grade in order to be able to solve those. But for right now, we're just going to work on solving by graphing. So that is enough information that you can get started on today's assignment. Practice graphing nice lines. Pick that point that works in both equations, the point where the lines cross, and then write it as an ordered pair. Important for you to do that.